seems like a day at this point, and I'm not sure. I don't even look at the date anymore. So, so thanks everybody for. This used to be called SANS at night. Now it's SANS at Mike. So this is kind of a different format. We don't have beers, at least not necessarily. But if you want a beer, you should go grab one. I cannot send you one virtually. We're not in that reality or time zone or whatever yet, or that part of human history where I can just virtually send you coffee, tea, or beer. So I apologize. So this is our SANS at night talk. I used to say, like maybe SANS goes wild. I can use cuss words or something. I don't know. But now it's just virtual. So now it actually gets recorded, which is a lot scarier because you can actually go back and watch this, and that might be good or bad. So that actually doesn't change whether I moderate what I say or not, but that could be good or bad. So anyway, without further ado, by the way, for those that have never used GoTo platform, I don't know what you would call this, go to webinar, go to meeting, whatever. There is a question and answer at the bottom, and there's a chat. I will try not to look at it so that I do not distract myself during the talk. Okay, but if you put questions in there or if you put chat in there, I will try to get to you after the talk at a logical point. Okay. Let's talk about complexity. Complexity in terms of exploits, okay? And so this talk is historic. Complexity for me starts at the Morris worm. And the idea here was that the original worms, the original exploit kits, the original things we did from an exploitation standpoint, payloads and exploits, were very simple, right? Morris worm used 4 exploits actually to deliver its payload, but they were really, at the time, they were novel and unique, but they were still fairly uncomplicated, at least by today's standards. So, in 1986, we have Smashing the Stack for Fun and Profit. There's a seminal work in a FRAC magazine by Aleph One. And then we have the whole conversation 2 years later, FRAC, around SQL injection and what that means to what we do today. We also have, just after that, with all the different worms and all the permutations of worms and all the different things that happened, Windows XP Service 2 comes out. And Windows XP Service 2, Service Pack 2, is a leap forward in security on a commodity or commonly used operating system like Windows, which for the business world was ubiquitous and for home users was starting to be ubiquitous. Shortly after that, or around the time frame, Linux and Vista, which everybody wants to forget was an actual operating system, introduced the concept of ASLR, or address-based layout randomization. We'll explain that in a minute. Somewhere around the same time, you have this concept of a ROP chain, and we'll explain why the ROP chains and ASLRs come around. Emmet is then introduced as another trampoline and in complexity for operating systems in 2009. And then somewhere around 2000 and somewhere after 2010 and the financial crisis, we have technologies that accelerate adoption of services in a different way. Docker is probably the thing you hear about the most. It's no surprise. We have around that time this concept of, or this renaissance in things like LOL bins and LOL bass. And in 2017, we have this idea of pointer authentication in your operating system, which leads us all to wonder, why have we been building exploits a certain way, and what does all these things have together? And the answer is very simple, right? All these things have very simple primitives that make operating systems go fast, and that we've been using to exploit the system for a while. And so this is the idea behind the system. And so my name is Moses Frost. I am a SANS instructor. I work at Cisco. I sometimes blog. I actually author 2 classes at SANS. I co-author 642, and I just debuted a new one, 588, Cloud Penetration Testing. And so this talk is Cloud Native Payloads. And for those that don't know what a Matryoshka doll is, I'll explain it in a minute. This here, I warn you that everything I say comes out of my mouth and brain and does not influence the corporate overlords that pay me. So please don't take it out on them. So why are we here? Why did you spend some time out of your busy day where you could be getting a haircut or, oh, never mind. Why are you here and not playing video games? And this is not even a question to drive you crazy. It's actually just, why are we going to be talking about what we're talking about today? And so to understand what the goal of this talk is, the goal of this talk is to give you an idea for what is possible and probable and why. My previous talks on the subject got very deep into the bits and bytes of this, but I stepped back a little bit and I wanted to give you the overarching topology, or at least a talk track, so that you understood where things are and how they work and why I have the thoughts that I have. By the way, I just call these Russian egg dolls. They actually do have a name. And it turns out the name is not Russian egg doll, just FYI. So if you've never played with one of these, they come really tiny too. They're really tiny size of things. So let's start with the first conversation. Smashing the stack. We mentioned it briefly at the beginning. If you look at a history of exploits, right, which maybe one day you'll have a historian, journalist go through this. The first exploits were pretty simplistic in nature, right? You had stack and heap. You had some basic pointer math that you did. You sent the pointer over to, you sent your functions over to something in the heap, and then what typically happened at this point was you could overwrite the return pointer in some specific way that would basically overwrite where the execution of the processor was, and it would inject your payload, right? And typically all the exploits that were written for this type of a system was designed around what the system expected at the time, which was a hexadecimal array of memory locations. And typically when you're dealing with that low level of a system, you're dealing with assembly, right? And so in assembly, you basically would construct your shell code or whatever the payload was, and then you would execute it. And because this was whatever assembly it was, x86, Intel architecture, it doesn't matter, right? Spark, whatever it was, it would typically do the execution that was stated, right? This happened for a long time, and this happened pretty frantically the late 90s and early 2000s, and which is why you saw an increase in the number of exploits that were for front-ending systems like mail systems, DNS servers, web servers were affected by this. Anything that would run on your OS, and because the operating systems were just dumb and they would execute whatever you told them to, this led to things like worms easily spreading and tons of viruses. And it was a golden age of simple stack and heap based buffer overflows. that you would find out there. Now, while going back to our talk track, which is around cloud native, who cares, right? You're going to see this idea that these really evil Russian dolls, honestly, who cares that these things are happening? But if you could digress for just 1 second, I'd like to talk a little bit more about history, okay? So with the advent of massive exploitation of things and worms came things like Windows XP SP2. And with Windows XP SP2 Service Pack 2, you had the idea of memory protection, canaries, and the like, and the semblance of an actual beginning of security on the operating system in the Windows world anyway. Now, at the same time, people were experimenting with the different ways that you can get execution to fire. So if you're not going to allow me to overwrite the stack and the heap easily anymore because you have canaries in memory, I have to find different ways of abusing the system. At the time, a very common thing that you could do was you could do these return to libc exploits or glibc exploits, where you could basically return the pointer not to the stack or the main stack, which may not be available anymore with all the restrictions, but you could actually return it to some kind of a libc library that you knew where it was loaded in the system, because everything back then was loaded in a very, very known location in memory. So you could say, hey, I want to call this location, and I want to actually bring up libc, and I want to call system, and then I want system to point to wherever I stuck my execution code, which could be, bin bash or whatever the operating system is, right? Command.exe. This meant that our exploits had to become a little bit more intelligent. With the advent of Windows XP Service Pack 2, as the last version of XP became the last version of Windows that used these legacy primitives, things got a little harder, right? But then my Russian doll still says, who cares, right? Well, we're getting there, right? We're getting to the who cares part. This is the part that is really important, right? Now, with Windows Vista, you get ASLR, and address space layout randomization really accelerates this idea that you no longer can have a very simple exploit and payload condition. Now, I will stop here for a minute and explain that there is a trade-off, okay? Any system that is low memory and has to do something very fast, so think of embedded systems where you're processing things hyper fast, gigabits of data or whatever, and systems that are low memory footprint and really low overhead for a processor because you're spending all that time, moving packets and the like. Those systems are not a candidate for ASLR. You probably will not see ASLR or any of these kernel protections enabled on these systems, because by enabling these kernel protections and the like, you actually are diminishing the performance of the machine. It just so happens that your commodity desktop at the time, even today, right, but starting about this time, had so much excess compute for its day that you could trade these things off without actually necessarily slowing down performance. It's almost like the backwards of the speculative execution bugs that you hear about today. Because we do speculative execution in the kernel, we get an acceleration in efficiency and performance, but we also lose security. And so by removing speculative execution in the hardware chips, you actually will degrade the performance of the box. And so it's kind of a backwards of that, right? In this case, Vista ASLR, you have so much excess capacity. By doing the address space layout randomization, the performance hit is not as noticeable as it is on, say, a terabyte router or something like that. So what is ASLR? Like, what is it exactly that you do, and why is it important to talk about it? Well, because you no longer can call the places in memory where you expect things to fire to be at, right? So nt-kernel.dll and all of the different links that would go back to calling the different DLLs that would allow me to execute, say, command.exe or whatever my payload is. Those linkages are not known to me because they're randomized on boot and they change every time you reboot the system. And from system to system, they're basically random. So this concept started back then, where you would have this idea of a chained exploit. And the idea of exploit chaining, for the sake of exploit chaining, it just so happens that when you have these multi-stage exploits or these multi-package exploits, you typically will need to find a bug in the system or know about a bug in the system where the process memory for the system is leaked. That leaked set of memory addresses allow your second stage payload to know about the locations of the parts that you need to construct, whether it's a wrap chain or it's just knowing where to load the DLL libraries for the actual components you need. You need to have more than one exploit, and today this is very true. You need to have more than one exploit to make things fire, to just make things work. And so this idea of chained exploits have been around now for a while, because you need one exploit that will give you the memory locations or whatever it is to land the next, to have the other exploit land its payload in the right location or call the payload from the right location. So this starts us off with our idea of the Russian dolls, right? It was my way of explaining that in a system you can have these package exploits, one inside of the other, and you could deliver these exploits whether it's delivered in 2 requests or it's delivered in the same request, just one package inside the other. The Russian dolls, nonetheless, this idea shows up, right? And if you want to visualize it a different way, you have exploit 1 that leaks the address. You have exploit 2 that just runs Microsoft Paint. I don't like calc.exe because everybody just uses calc.exe. So somebody once told me that, actually Derek Rook once told me, you really haven't hacked until you've started hacking with Microsoft Paint. So Microsoft Paint it is. But this still leads us back to, what does that have to do with the cloud, right? And so this whole time that we've been talking about these payload packages, we still have been talking in a roundabout way about one thing, and that thing is C, right? So the C language is still the language, a common language that is used, C, C++, and C derivatives and things like that, but it's foundationally the common language that is used when you're talking about kernel level, driver level, systems level exploitation, right? And so when it comes to this, C is still the dominant language, okay? So before we get into our exploit 1, exploit 2 environment, we got to talk about how does this work with cloud native and why do I care? And so I want to bring you to the next topic, right? The more important topic, right? Which is kernels. That entire conversation that we just had is that kernel exploitation is become really hard. And the operating systems are getting more difficult to try this systems level, kernel level exploitation, such as stack smashing, heap exploitation, wrap chains. They're just getting hard. So what are the bad guys doing to try to win when this is the environment? So we've got a couple of options. One option is to get hardware exploits to fire, right? This is how that whole speculative execution thing got so much work, is you're now going underneath the operating system and abusing the way that the hardware works in order to leak memory, maybe that's part of the ROP chain that we talked about, or just to leak information out of the system that we could use to, say, get into a system somewhere else, right? You could use a speculative execution bug on Windows to leak the hashes of memory so that you can get an NT hash. It's pretty easy. The other thing that people were doing is they punted and they said, you know, Windows and Linux, I mean, I would say, I would argue the Unix graybeards did this very well for years, but Windows ships with a ton of executables, right? And if you ever looked at Windows System 32, Windows System 32 has hundreds of executables. And so for years, people have been cataloging all of these executables and figuring out what their underlying functionality is. And it turns out that certain executables in Windows will actually let you download and execute software when you didn't expect it to be able to download and execute software. A great example of that is the Scraba objects or the Scrably attacks, where you basically use the SCR obj DLL, which is basically a script object DLL, to execute your malicious DLLs and load them, to download and load these malicious DLLs. And because it's not an executable that you would expect, it might not be blacklisted, or it might not be in that white. It might be in the whitelist. Just different things that people have done. So LOL bins, or living off the land bins, or binaries, LOL baz for Linux, right? These are all valid mechanisms to say, you know what? It's too hard in Windows to try to do exploits, right? I mean, there's some really good ones that have come out lately, but it's really hard and rare. So why don't we do other things? Why don't we abuse the network sockets, abuse RPC, abuse name pipes, abuse the way that Exchange executes, right? These are not programmatic C-level exploits as much as they are abusing the architecture of the system, right? And so we've had to diverge from what is commonly known as a simple Stack Overflow into something like this. The other area that I would argue has a lot of win is application bugs. Application bugs are way easy to exploit, right? And we'll show you why here in a minute. But with an application bug, you're sitting at another abstraction layer, right? Because the application is typically running on top of a binary, and it could yield you some interesting results. And applications are pretty much everywhere. If you talk to any major company, they are but a series of apps, right? I famously joke about Berkshire Hathaway, because if you've ever seen the Berkshire Hathaway website, it actually looks like it was built in 1994 and never updated. And so you can argue very well that there is no Berkshire Hathaway app, even though they are a billion-dollar investment company. But for the most part, many other applications today are filled with apps. They are app companies on top of physical companies, right? Whether that's a Coca-Cola, Pepsi, or it's a supermarket chain. If you've ever used something like an Instacart, right, where the supermarkets actually are delivering the groceries to you, I would say that is as much of their profit center as anything else, right? We call these things, by the way, omni-channels. So if you ever heard that in a financial sense, you have your physical retail store, you have your e-commerce, and if you have both, you have omni-channel. That's the idea there. But yeah, we interface a lot with these applications. So let's talk about why these are fun. Typically a web bug or an application bug, and for the most part, most applications today, not all, but most of them for the majority are doing some kind of a web transport. Typically for a web transport, you are appending a string to the end of another string, right? It's almost like a format bug. Now there are very difficult web bugs out there. You have everything from deserialization attacks to a format kind of attack. So you even have memory corruption bugs that affect the underlying interpreter. But the memory corruption bugs that affect the underlying interpreter, you go right back to, hey, we're using C and we're using C primitives and we're going back to assembly and things like that, right? So typically not necessarily classified as a web bug, but can be, right? And so now that we talk about these web bugs, we can now start talking about what I feel is going to be the next 20 years of exploitation from the moment that someone else figures this out, right? And so we're going to do a quick detour. Don't get mad at me, Russian dolls, little Russian egg dolls. I'm going to do this detour, and we're going to talk about something real quick because you need to understand it in order for me to understand cloud stuff, okay? So first of all, there is this concept of cloud native, all right? And we really need to understand what a cloud native application is for me to talk about exploitation and cloud native payloads, all right? So the Cloud Native Foundation, or what they call the CNCF, or the Cloud Native Computer Foundation Charter, they have this concept of like, what is a cloud native application, or what makes something cloud native, right? A cloud native is basically it's got, so if you've never seen the charter, by the way, like every good charter nowadays, it's on GitHub, so you can pull requests and update your charter. And it's got a bunch of things in it, so it's not just these three things, but I distilled it to three things to help you, right? So one is the applications are typically container packaged, right? So no more tarballs, no more war files, no more jar files, right? You want my app, it's in a container type of delivery vehicle, okay? Well, that's easy, right? Because all I need is a container runtime, and I can run my container ubiquitously across any system. Okay, that's great. Dynamically managed. Well, what does that mean? Dynamically managed basically means that the system is managing the packages in a very dynamic way. So Kubernetes, Docker Swarm, right? The idea that I can upgrade my container with a hitless upgrade or with a staged upgrade, that's what that kind of means. And then microservices oriented, and that's where this talk really takes off, is the idea that I don't have to bring you a monolithic stack, and I will show you what a monolithic stack looks like here in a minute, but I don't have to give you this monolithic stack. I can give you this microservices stack, right? That's what a cloud native application should be, all right? So let's break this apart. Containers, right? This is an example of you being able to go to your local computer, and by the way, I made up the name of the container, so don't try to get it. I don't know if that exists. But the idea would be, you would go to your computer, you would say, Docker, I want you to execute interactively with a container. The T means container name. I want you to interactively execute this container. Nmap underscore container is the name of the container. Don't try to download that because you could always be downloading a backdoor container. That's a whole other thing, right? What is the command line that I want to execute inside the container? I want to execute bin bash. By the way, that's wrong. I should be executing also slash whatever slash nmap, but you get the point. Minus p80 1.1.1.1. I could also just have it execute the container, and as part of the container itself, it knows that it needs to execute bin bash nmap, and all I got to do is pass the arguments in it, right? And then Docker will say, sure, I'll start the container, I'll scan 1.1.1, and I'll exit. And the reason that it does this, and I'm going to digress here for like 2 seconds about containers because this is very relevant. The reason that it does this is because a container is a very, very, very simple set of primitives in Linux, okay? A container basically uses the Linux kernel to declare a namespace and a control group, okay? And every process that lives off of that namespace and control group believes that the top of the process directory is itself. It doesn't know about the other processes around it. Also, because the container does a chroot or chroot of itself, of wherever it's running, it believes the file system that it has is all that exists on that disk. So using things like bridging on the network, chroot, and basically Linux control groups, you can create your own containers. You don't have to run Docker. You can do them just from the Linux OS itself. Probably don't want to. It's probably like 15 or 20 commands every time that you want a container, but it can be done. And so a container is not magical. It is just an organization. It's for operations and organization. It is not necessarily for security. But it's handy, right? Because I could take a Red Hat container and I can run it in Ubuntu. Because what makes Red Hat different than Ubuntu? Userland, right? Pretty much. So I could say, hey, I want a Red Hat 9 container. God, Red Hat 9. But I want a Red Hat 9 container, and I want to run it inside of an Ubuntu 2004, and it would do it, right? And so that's what makes it kind of fancy, right? And super portable. If you haven't checked this out, Metasploit comes as a container. You can just say Docker run Metasploit, and you have an official Metasploit container, and you don't have to worry about Ruby and the Ruby dependencies and bundle exec and all that other animal excrement that has to there that you get with dealing with dependency hell. Okay, so what? Like, why do I care about containers? Well, this is important, right? I can build, just think about this from an operations standpoint. As a developer, and I'm a bad developer, right? But as a developer, I can build my software package on my desktop. You basically put the container in the Docker Hub, and you can pull it down and run it and not have to build and not have to have dependencies. And you can build tons of them. You can actually say, I want 20 of the same container. Doesn't matter, right? And as when you kill the container and you boot it up, it forgot all the stuff you did in it, right? So it discards all that, right? So it's like immutable, okay? That's what makes these things really, really, really nice. Because as a developer or as a DevOps person, I now have a simple way of rolling out software. So what does that have to do with this cognitive payload? So here is the idea of a microservice. Now this is where you really have to understand what's going on in order for you to understand my payload conversation, right? So here's the idea behind a microservice. So today I have a microservice application, and for some reason, whenever you want to learn this stuff, and don't ask me why, it's kind of like whenever you want to hack, you learn with Hello World. The Hello World of app development is they always want to build a Twitter app. I don't know why. They always want to build a Twitter app. So let's say you build a Twitter app, and the Twitter app, when you build it on your computer, it has a couple of functions in it, and the functions are mail, and the function is user, and the function is tweet, right? And you can pick your favorite language. I don't care what language it is. I'm gonna just pick one out of random. I say, you know what? This is a Ruby on Rails app. So I just say Rails new. It's a Ruby app, and it's running this thing. And even if I containerize it, all these functions live in a file in my Ruby app. All right, great. It's fantastic, everybody. Right? And this is the way that we have been building applications forever, right? And so what happens is you build an application, you build. During this whole crisis that we've been seeing, unfortunately, in the United States, what you've noticed is people saying things like, well, we've got this really old unemployment system written in COBOL, right? And people jump up and down and go, oh my God, COBOL, like, why would you do that, right? And there's all sorts of really good and bad reasons for COBOL. But at the end of the day, it's probably a gigantic application that's been built over hundreds of thousands of man hours, right? This is not an application that you're going to throw away. This is not an application that you're going to format tomorrow. And every time you want to make a change to this application, the application is so massive and so big that you start to have to do these really onerous things. Oh, you know, if I change the app, I've got to go in there and I got to test all these functions because in my example, the tweet function can mess with the mail function, can mess with the user function. What a disaster, right? And so over the years, as containers became more and more relevant, people decided to decompose their application so that they can have different containers for different parts of the application. And this makes total sense, right? Because if you've got a big load on the system and you need to send out 1,000 emails, you don't want to bog your application with going through the mail function and having to optimize it and rewrite it and redeploy it, right? Think about a system now where every critical function of your application is its own app and its own container, right? It makes total sense because if I need to send out 100,000 emails immediately, right? I can now take a Lambda function that's running my mail app and I can have 20 of them, right? And I don't have to have 20 of this app over here. You know, I don't have to go back and have 20 of these and figure out 20 of these monster apps. I can have 20 of these little itty bitty, teeny tiny, and I'll just do this instead. I can have, you know, 20 of these, right? It's great. Or if I have a big load on my user environment and I need to scale 20 containers to handle load for the user, I can do that and then discard them later. And they're containers, right? They're immutable by nature. They spin up, spin down. I can use a load balancer. Really handy to do it this way, right? And then somewhere along the line, you realize, well, you know what? My application was written in Rails, right? And I mean, I'm a Ruby fan. I love Ruby. Ruby's been fantastic. Python's been fantastic. Nobody should like PHP. JavaScript is a nightmare. It's why we can't have nice things in the world. But anyway, these things are out there and they're used. Right? They're used everywhere. You typically don't have a say, right? And what gets used, the whole team picks a thing and you just kind of run with it. Now, all great and dandy, but let's say that you decide that a specific component of your application is running slow. And, you know, this isn't the old Twitter where, I don't know how they did it, but old school Twitter, they would do things like, let's write it in Rails. And then they would say, no, let's write it in Java. Okay, forget that. Let's write it back in Rails, right? This isn't the old school Twitter. This is like the new one, right? And so you wouldn't do this, right? You wouldn't just rewrite your whole app. So if you found that you had a very, 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 very slow function, couldn't you just ship that container with something else, right? Couldn't you just take that container and run a different process? So now I have Ruby on Rails here. I can make this one Go. I can say that this is now Google Go. And I can say that this is Node.js, right? And I can replace the slow part of the container with Google Go. And now, you know, Rails talking to Google Go, really what that means is maybe it's an HTTP call, right? But I can rewrite the parts of the application that I need to rewrite in a different language, a more performant or more purposeful language, right? And then I can go ahead and ship that container and I'm off to the races. But now we're on the attacker side, right? What do my attacks look like in this case, right? Well, it turns out that the attackers, and by the way, I call these polyglot exploits. Should have said that ahead of time. I call these polyglot exploits. For those that don't know what polyglot is multi-language exploits. So I just put it up here. So call these polyglot exploits, and the idea is I may have an initial entry point starter exploit that runs inside of a Ruby package. Inside that exploit, once I exploit and take over whatever, the second part of the exploit is packaged inside, which might trigger going to a different container, which reads in a, I don't know, a Go exploit, which might execute something on Node.js. But the idea is I might be going across multiple containers, and if it's all HTTP, that's fine. It's really URLs and that junk. But if it's not, if it's actually platform-specific execution, I'm going to have to figure this out, right? And so the complexity now is going to change from appending strings to the end of a web application to having to consider that I might be sitting on a heterogeneous system with a single language, or I might be going from container to container to container across multi-languages using polyglot exploits. And so this brings you to some other considerations, right? First thing that you have to think about is that you have this concept of strings made your web application hacking simpler, and having to do pointer math and hex math was hard, right? Now you also have to think about this concept of an egg hunter, right? So in original, the original exploits, they used to have this egg hunter concept where they would try to figure out how to line up the memory addresses and figure out how many no operations or whatever lined up the memory addresses so you knew how to execute code. When it's all one system, that's great, fantastic. But now you got to think about, well, my new egg hunter, my egg hunter NG, if you will, my egg hunter next generation is going to have to compensate for, I got to go cross system, cross container, cross language, right? So it's pivoting across different disparate things. And so transporting even the strings become a challenge, right? So some of the stuff, some of the early work that I did, how you put the quotes in the string and what characters escape, completely different between libcurl and the command line version of curl. And so whether you're sitting in a URL or you're executing in a bash prompt, that's all different. And so the string concatenation and the string manipulation is all different. How many times you encode, decode, all different. And so all these things are difficult, to say the least. And also, and so I almost forgot to mention, there's also this concept of new protocols, right? And so what does that look like? And so you could have a front-end system in which your delivery vehicle is HTTP. And you're like, yeah, I know HTTP. HTTP is what I use in the URL bar. It's great. It's fantastic. Or you could have a newer protocol like Google's gRPC, which is a binary format that's sitting on the wire, very popular, right, inside of cloud environments. And you may have one part of the transport that's delivered over HTTP and URL encode decode, and you may have another part of the exploit which maybe is delivered over gRPC, completely different protocol format, completely different way of delivering it, more traditional binary deserialization kind of concepts. Not that there's any issues with gRPC that I have found yet, but just saying these are the different protocol delivery vehicles you might find, right? And so where you thought you had one black box here because you didn't have source code, you didn't have all these things that you were used to, you may have an even more kind of a black box environment where you have less visibility, less telemetry, less, but there still are vulnerabilities there, all right? And it's unearthing those that become interesting. By this point of the talk, you're probably thinking, are you serious, right? If you don't know who this is, I love this meme. This is the "Are you serious" guy, and his whole meme. The whole meme is to question this person is out of his damned mind. Uh, but I'll leave you with this, okay? Technology builds upon itself, right? We don't go from a world of stack-based overflows to wrap chains overnight. Okay, you have to step your way and build your way into these technologies. So that's not a stopping point, right? And what seems impossible today might not be so impossible given enough attention to the problem, right? This is where innovation comes in. I'll leave you with a quote, one of my favorite quotes. Any sufficiently advanced technology is indistinguishable from magic. I will also say that I've changed the quote slightly to say that any sufficiently advanced set of exploit primitives is also indistinguishable from magic. And so just kind of wanted to put that out there because it's kind of true. Um, so where do that leave us? I give us a good 5 years before people start figuring out what the hell I'm talking about. And so the idea is that you, as somebody listening to this, somebody thinking about this, could be the person that says, well, you know what, I'm going to take this piece of research and I'm going to append to that and I'm going to make something out of it, right? And then the next person takes that chain and grabs the baton and says, yeah, but you know what? I bet you could do X, Y, or Z with it. Or did you know that strings, here's all the ways that strings get manipulated differently in the different languages. And just things like this, where the research feeds on itself, is only more valuable, right? So my call to action is, go forth and build stuff and break it and know what cloud native is. And I've got little demo scripts and things that I kind of go through. And I'm baking this into the cloud pen testing class, where we have a small section on polyglot exploit primitives between containers. It's a very small, narrow section of the class where we kind of give people a small taste of it. But I want to give you a background behind the thinking of it, because most people have not been exposed to this kind of thought process, but it is totally valuable. And so this is one of many talks that I've given on the subject. This is probably the first time I get it virtually and to such a recorded audience. And so this is cloud native payloads. And so I call these, an evolving talk series. You can find me here. Come take a class if you want. If not, I'm an open book. You can always ask me. And I'll leave it open for questions. There is a Q&A panel. I like leaving 10 minutes open for questions in the Q&A panel. And there is also a chat. So don't be shy, and you can fire and kind of ask away. Oh, and by the way, Carol has posted the evaluation in here. And so you're more than welcome to evaluate the talk as well. And actually, let me, what did I do? I don't see the Q&A panel. Did I misplace the Q&A panel? Give me 1 second. Let me make sure I get out of here real quick. And I don't have any idea where I put the Q&A panel. It's probably hidden back here somewhere. Maybe it's here. Nope, that's not the Q&A panel. Oh, it's back here. Found it. Found it. I'll leave this up so that I usually get asked, oh, can you leave this up? And do you mind sharing? So I'll leave this up. We can just stare at each other. I could play music. I think that's always much more fun if I just play music.
Moses, is there anything you need from me?
I don't think so. I'm just giving people an opportunity to ask questions, but if there is no questions to be asked, then I'm perfectly okay.
All right,
Should I make
shut it down.
should I yeah, should I make these questions? I can just delete these here. And I can delete that one there. I had some questions that I sent you earlier. Okay, yeah, all right. Shutting it down. So if anybody wants to reach me, you can always reach me here. All right, Carol? And by the way, happy to see Saki going so well. Wash your hands, everybody.